We're about to embark on about 3 weeks of studying the discrete abilities of WebGL, and this is one of the most exciting areas in computer graphics right now, and there's a lot of new material here we're going to be studying, a lot of which wasn't even possible to do even a few years ago. But we'll start kind of gently and talk about buffers in a little more generality and just talk about what do we mean by a buffer, and how to, in particular, how do buffers relate to images. We have data stored in a buffer that's, for example, the frame buffer. That's a picture of what we're going to see on our display, but we also have things like GIF images and JPEG images that we deal with on the web, and so what's the relationship between them? And then for WebGL, we want to know how we get information from the CPU to the GPU and back, and how do we get information that might come from, say, somewhere on the web, like a JPEG image, and use that as part of our of an application, and it'll eventually be part of a rendering. So all of these issues are going to come up in the next few weeks. But let's start very simply and say, okay, what's a buffer? And from our perspective, a buffer is a block of memory which you can think of as being three-dimensional, that it has two of the dimensions, the M and N here, are the height and the width of the buffer, and that gives it its spatial resolution. But it also has a number of bit planes. We can look at it that each of these planes represents one bit. So you have, if this was, say, a 1024 by 1024 image, there would be 1024 by 1024 bits, and you could address each bit by giving it an ij in this plane, and we'd have a bunch of these bit planes lined up behind each other, and the number of bit planes, the k here, would be its depth. So the typical numbers you'd see were buffers that were 1280 by 1024 or 512 by 512, the standard numbers that you see. And the standard depths would be, for a whole image, we would have 24 or 32 bits for an RGB or an RGBA image, or just talking about 8 bits, which would be more typical to talk about just the red component, the blue component, the green component, or the alpha component. But if we're talking about single bits, which come up a lot when we're doing interactive kinds of things, usually not within WebGL now. We used to do them within OpenGL, but now we can use other methods. But if you're talking about a single bit, then we tend to call this a bit plane, and that we have 8-bit planes for typical 256 possible values of a color component. Now, we also have different buffers. We've already seen some buffers, so the next question is what buffers does WebGL support? Well, we've seen 3 of them, and I'll talk just briefly about the 4th. We know that there's a front buffer which is the one that's displayed, a back buffer, which is the one into which we draw into while the front one is displayed, and then they're swapped. These in WebGL are under the control of the browser and the operating system, but we can think of them as part of the frame buffer. So you say, what's in the frame buffer? Well, there's a front buffer, a back buffer. Then we know that there's a depth buffer, which, depending on your system, is probably 16 or 24 bits deep. It's probably more typical now to have 24-bit deep depth buffers. And finally, there's a stencil buffer, which we won't be using in this class. That's usually about 8 bits deep, and we use it for applications like overlays and things like that. We can save information and then look at what's in the stencil buffer and use it as a kind of mask. So where something is set, we put image data there, and if it's not set, we don't put image data. But there's a variety of very special techniques you can do with the stencil buffer. So these are all defined as part of WebGL and the WebGL frame buffer. But it's probably easier to talk about the individual buffers. So rather than talk about the entire frame buffer, we'll talk about the front buffer, the back buffer, the depth buffer, and the stencil buffer. And I don't think that'll really cause too much confusion. Now, the next question is, where are those buffers in your system? Well, we'll talk about it in a modern system. Those buffers are going to be under part of the HTML5 canvas. So that's got the default front and back canvas, front and back buffers, and as we've said, that's under the control of the local Windows system, and typically you're going to find those on your graphics card. The depth buffer and the stencil buffer will typically also be on the graphics card. And as I said, we're not going to talk about the stencil buffer here. Most of these buffers are going to be 8 bits deep. Each component will be 8 bits deep. So we'll have a 32-bit front buffer, a 32-bit back buffer, probably a 32-bit depth buffer too. Now we'll also see a little bit later that we're starting to see floating point buffers, and there's a lot of reason for that when we start talking about frame buffer objects in a week or two. We want to be able to do more accurate computation, and the 8 bits per component in the typical frame buffer is just not enough to do a lot of things that we want to do now. So we're starting to see 32-bit deep buffers where that buffer holds an IEEE standard floating point number at each XY value in the frame buffer. Okay. Now there are other buffers that we can talk about. These are buffers that used to be in the standard fixed function OpenGL, and it's worth going over them to see the kind of functionality that we want to have and how it was implemented previously and how we're going to implement it now. So one was to have extra color buffers around that were called auxiliary buffers. Well, one example of that is if you're trying to do stereo imagery, then you'd want to have an image for the left eye and an image for the right eye, so you'd need probably 2 buffers more, one for the front right, one for the back right, because we're still going to want to do buffer swapping, and one for the front left and one for the back left. So they were provided. You could also use them for other techniques that we're going to be seeing when we do render to texture, principally things like picking, where you want to be able to point to an object. You could use an auxiliary buffer to store some information as you render the scene. There was another one that was provided called the accumulation buffer. The color buffers were often pretty fast. They were on the graphics card. The accumulation buffer was kind of a floating point buffer that resided inside the CPU side. The advantage of it was that it could do floating point operations. So we started moving to the point where we were doing image processing kind of operations, where you do things like filter. You replace a value by some combination of the values around it. You're doing arithmetic on a group of pixels, and in order to not have tremendous round-off errors in that calculation, you really want to do it in floating point, and the way that was done then was to create a buffer on the CPU side which would support floating point operations. The difficulty with these was that it was really slow, because you were sending information back and forth between the CPU and the GPU, and typically on most implementations then, especially PC implementations, the paths were not symmetric. The path from the CPU to the GPU could be fairly fast. It would have a lot of parallelism, while the path back from the GPU to the CPU tended to be slow. And if you were doing these kind of operations with an accumulation buffer, even though they would work, they would be very, very slow. So they're now deprecated because of what we can do with techniques like frame buffer objects and render to texture. Now, if you look at where the memory is on the GPU side, you've got multiple kinds of memory there. So there's memory that's attached to the GPU on the graphics card. So that'll be, sometimes there'll be texture memory. There'll always be texture memory where you can store a lot of texture images. There'll be memory in the GPU itself, and there may be some more memory there that you can access from the GPU. Some of the advantages of this is that this memory is not going to be under control of the Windows system. There may be some floating point buffers out there if you have a high-end graphics card, so it increases the flexibility you have to create more interesting applications without the loss of speed, because you're never leaving the graphics card with these images until you may want to at the end bring them back and save them somewhere. But the major operations on images are going to be done exclusively on the graphics card. Now, the next thing is, say, well, what is an image? And that gets a little bit confused at times, because we say, well, the frame buffer contains some sort of image because that's what we see on the display. We have an RGB or an RGBA image there, and typically, as we've said many times, that'll be probably 1 byte for each component. Those images go directly to the display. There's no compression involved, so they're very straightforward. There's no formatting information saved in there. They're just a block of bits, three-dimensional block of bits that's displayed. Now, on the other side, when we work with web applications, where most of you are probably familiar with a number of different kinds of images. We have JPEGs that we get from taking pictures with standard cameras. We have GIF images, which have been an internet standard for a long time. PNG images, and a bunch of others. Now, there's problems there in a couple of ways. One is that these images, like for example JPEGs, are a compressed type of image. That it's not a simple here's the location X, Y, and here's the bits there. The image has been compressed to reduce the storage, usually by an enormous amount, because images have a tremendous amount of redundancy. There's a bunch of information in the text about that I won't go over here. So not only does it require some sort of conversion to go between that and a straightforward RGB image, because there's all kinds of different formats. WebGL, the developers just throw up their hands and say, well, we're not going to deal with that. That's up to you and your application. You have to figure out how to convert from the standard formats to RGB images. Now, there's one exception to that in WebGL that was not in earlier versions of desktop OpenGL, and that's for the sum of the standard web types. So when we're dealing with textures, as we'll see in another few lectures, we can directly use a JPEG image, and WebGL will uncompress that image and put it into a texture map for you. But generally you're going to have to either find some code on the web or develop some code if you're working with some image formats. Like if you're dealing with a TIFF, what do you do to get that into it? Some of these are very easy to deal with. There's a lot of software out there on the web to do your conversions. Okay, now I want to give you this one slide that I saved from the older version to show you that kind of the operations that have to go on in general when you're bringing image data into an application and then trying to get it out again. So this is truly a desktop OpenGL point of view. We can emulate it, but this will give you an idea of some of the issues that arise. So if you start off over here with your application, so that's processor memory, you have some sort of a standard image in some format. You've got to unpack that image into getting pixels that will be understood by the graphics system. You can also do some mapping that changes the values. You may want to, if you have, say, something like a luminance image, which is all black and white, and you want to make it brighter, or you want to spread the gray levels out to increase the contrast, you might have a map that does it. You might have, if you're doing index color, which we'll talk about at some point a little bit, you'll have a table that will convert essentially grayscale values into RGB colors. There'll be a bunch of testing that you can do that is in fixed function OpenGL and desktop OpenGL, where you can look at pixels and decide what to do with them. For example, you may want to look at the transparency, the A value, and based on that, throw the color away or include it. But eventually, after you go through this series of operations, finally, data from that image that you started with will work its way into the frame buffer. Now, once you've done your processing and you want to get it out, now you have to go and put it into a standard format. So you got an RGB or an RGBA image here, and now the operation is called packing to now put that into one of the standard formats that you can use on the other side, like convert it to a JPEG or a GIF or some other standard form. So this packing and unpacking has a lot of aspects to it. One is the image that you start with compressed or uncompressed? Compressed images a little more difficult to get into an RGB image, but on the other hand, they save you lots and lots of space. There's a nice example in the text of just compressing one of our standard images to where visually you can't really see the difference between the compressed and uncompressed versions. Index color and RGB color, it's the difference between having all of your pixels be specified directly by their RGB values, or have them specified through an index into a table. That'll arise a little bit later when we talk about some techniques for doing things like pseudo-color, when we talk about some image processing-like operations. But formerly, that was there because it saved a lot of memory. The idea was that the analogy comes from painting, where a painter could produce an infinite variety of colors by mixing paints, but at any one time the painter has a limited number of brushes, so he will be using only a limited number of colors. So you can think about the number of brushes as being indices: brush 0, brush 1, brush 2, and each of those are mapped into a particular mixture of paints or RGB colors, so that the image is stored by its indices, but you get the full potential spectrum of the color, although in a typical setting where the indices are 8 bits, you can only have 256 different colors at one time. So that was important when memory was more expensive and slower. It's less important now, but it's not as a storage technique, but it's still important as a processing technique for displaying images. You also can get into colors with packing and unpacking. Things like, not only is it an RGBA image, is it a GBA image? What is the order, which is different for different systems, and how are the bytes in a 32-bit integer arranged? Are they little endian with the least significant byte on the left, or big endian with the most significant byte on the left? So those things are options that are there when you pack and unpack with desktop OpenGL. Now, we don't have, as we said, we don't have most of these functions, and we don't use them anymore. I think you'll see one instance of it later when we get a function off the web, when we use a JPEG, or I guess I'm using a GIF in one of the texture examples we'll see later. But one thing to keep in mind with all of this discussion is that you can implement almost anything you want of what used to be in the fixed function pipeline by writing the necessary code within particularly a fragment shader. There were a couple of functions, just to mention, that were in desktop OpenGL that were now deprecated. In a way, I miss them, but they were not. They didn't run very fast, and they could be done other ways. But there was a function called draw pixels, where you would give it a block of RGB or RGBA values and just tell it where in the frame buffer you wanted to put that block. So you could manipulate it with one function would move this whole block. A related function was copy pixels, which would take a block of pixels in one part of the frame buffer and move it to another part of the frame buffer. But you also had functions which operated one bit at a time. So the GL bitmap function would operate on a bit plane, one of the planes that comprise the frame buffer, and it would and you could use it pretty much as a mask by either it would write a color or do nothing depending on whether the bitmap had a 0 or a 1 at a particular position. So they were kind of nice, but as I said, they were less used. And a lot of the reasons that you would use them, you would now do that by some other package that you would use within WebGL. What it does remain is the ability to read values back from the buffers, from the frame buffer. And later we'll talk about reading from other buffers, but now let's just think about reading from the front buffer, and there's a function GL read pixels that will let you do that, and it's going to return RGBA values, and you can then take those RGBA raw values and put them in any format you want and do the packing and unpacking. It tends still to be a slower operation. The place there are two places where you'd probably use it. One is if you want to really do some processing, get an image and then save that image. You want to pull it back to the CPU and store it somewhere. The other place we'll see it is when we do picking by doing a special re-rendering in colors, and then we want to read the color at a particular location. Just read one pixel, and we'll use that there every time we want to do a pick, select an object up on the display. So we'll see more of that, but it'll be, as I've said, through texture functions and off-screen rendering with what we call frame buffer objects. But here's the function. It's pretty straightforward. GL read pixels. You say where do you want to start in the frame buffer? How big an image do you want to take? And then you have to say what's the format, and typically it'll be RGB or RGBA. Actually, I think in WebGL it has to be RGBA, and then you'll give it what format are they in? They're going to have to be unsigned bytes. I think that's required in WebGL. There's more flexibility in desktop GL, but images in WebGL are RGBA, and everything is organized as unsigned bytes. There may be extensions in some system you're using, but this is the only possibilities standardly. And then you give it a pointer to where you want those pixels to go. Okay. Now, finally, one other thing to mention here is we'll be seeing a lot of this. It's off because we're working in JavaScript. It's usually easiest to create an image that is just a one-dimensional array that has the right size, and just say, well, how much space do I need? Well, if this is a 512 by 512 RGBA image, then I'm going to make it 4 times 512 by 512 in my own code, and then do what I need to do to convert those values into whatever format I want to output. Okay, so finally, just want to mention again that one of the things that's changing is due to the fact that GPUs have a huge amount of memory now, and they're very fast, and that's why a lot of the former stuff has been deprecated. And the way we're going to do it is through frame buffer objects, which like other objects we've worked with, vertex array objects, there's going to be a present frame buffer, and there'll be other frame buffers that we can define as through frame buffer objects, and we can then write into those other frame buffers and read from those frame buffers. They'll usually live in texture memory, and that's called rendering to texture. And the applications we're gonna look at is, first we'll look at some image processing applications, and then we'll generalize that to look at what's called GPGPU, which stands for General Purpose Processing on a GPU, because we'll try and harness the enormous floating point power of a GPU to do operations which are not necessarily graphics. They can be something like multiplying two very large matrices together. Use the floating point power of the GPU to do that. So those are things we're working to. This is what I want to do first, is talk about texture mapping, and then we'll work our way up to talking about rendering to texture.